Hello, everyone. Okay, welcome back to now lecture 10, and we're going to wrap up what we were talking about last time, some questions dealing with gas equations. Okay, so now let's calculate the molecular weight of butane. If we have a certain amount of it in grams, fills this flask here at a temperature of 24 degrees Celsius and a pressure of 742.6 millimeters of mercury. Okay, so what you should do first is you should definitely convert your temperature to kelvins. You cannot do these gas laws correctly if you do not convert to Kelvin, because the Kelvin scale is the absolute temperature scale, so it goes from 0 Kelvin to a positive number, whereas Celsius and Fahrenheit can go to negative numbers, and we do not want negative numbers in our calculations. Okay, so that's why we use Kelvin. And then we converted the millimeters of mercury to ATM. So now let's just write everything we have here. So our mass is 0.5813 grams. So there's a lot of information here. So we should try to hone in what do we need for this problem to answer the question. So our volume here, let's convert it to liters. So this will equal to, this will be equal to approximately, or to 2,500 liters. Please keep all the sig figs. Do not omit any that will mess up your answer. Okay. Oops. 1 second, please. Accidentally shut off my screen there. Okay. So we have 24.4 plus 273. Okay. Okay, so when we actually do these calculations, it's okay to use 273 for your measurement, but maybe in our cases we should keep all the digits. So in this case, this would round to 297.6 because we are using addition and subtraction rules here. So we're going to round to the decimal place, to the least number of decimal places here. Okay. All right. So now, lastly, let's do our pressure conversion. So we're doing these conversions because I won't necessarily give you the conversions to ATM. I won't say, oh, this is equal to this much ATM. So I might not get that. So we need to do these calculations here. Okay. So we get approximately 0.9771 ATMs. Okay? All right. So we need to find molecular weight. We have the mass. So we need to find N. So need to find moles. Right? Because we need to know what's the molecular weight. So if we have the mass, we need to figure out how many moles are present. And if we could do that, we can figure out the molecular weight of our gas. Okay? So we're going to solve the P equals nRT equation. So we're going to solve for N, which will be PV over RT. Okay? All right, so if we solve for N here, we will get 0.9771 times So you can feel free to put in the units. You don't, I necessarily won't take points off if you don't. But as long as you put the units at the end, what we should have at the end, then you'll be good. Okay? All right, so that's temperature, gas constant, volume, and pressure. And we get 0.01001 mole of butane. Okay, now if we divide this, so we know molar mass equals 0.581 grams. Divide that by the moles of the gas present. We will get 58.07 gram per mole. So there you go. There we have it. So that's the amount of moles. That's the molar mass of butane in our sample. Well, it won't matter. Like the molar mass will be the same for any sample, but that's how you would figure out the molar mass. If you didn't know how much the identity of the gas, you can actually figure out the molar mass, given that you know how much gas you have in the sample and recording the other variables. Okay, so that's how you do that problem. Okay, let's move on. Now let's try calculating density. Okay, so we can calculate density in a few ways here. Okay. So the other way you could do this, I want to go back a little bit here. So for this problem up here, you can also solve it a little bit differently, and we could rearrange the PV equals nRT equation. Okay, we could rearrange it to solve for molar mass directly, actually. So we know N equals mass over molar mass, so you can substitute this in for N here. Okay, so we could do PV equals mass times RT over molar mass. And then you can solve for molar mass directly here by rearranging the equation. So that might be a more efficient way to do this, but either way would work. You would get the same answer. Okay, now let's calculate the density in grams per liter of oxygen gas at 0 degrees Celsius and 1 atm. Okay, so there's two ways to do this. I'll do it the quick way first. So we have PV equals nRT. So there's two ways you could do this. You can actually rearrange the mole equation. Oh, you can actually rearrange the equation to solve for density directly. So we know density is mass over volume. Okay. And we know moles is mass over molar mass. So we could rearrange it like this. PV equals mass over RT over molar mass, and then multiplied molar mass times P times V. So that's equivalent there to MRT. Okay. Then we could divide both sides by the volume here, and we get M times P equals MRT over V. But you see here, this M over V here is equal to density. So we can rearrange this equation to molar mass times P equals density times RT. And then rearrange density now and solve for density. And we get molar mass times P over RT. Like that. So we can plug those values into the equation and it should give us that value. But I'm going to now show a different way. We can first rearrange the PV equals nRT equation and solve for NV. So if we solve for NV, NV would equal RT over P. So you see NV, this stands for molar volume. So if we find the molar volume, we can change it to the actual density by just converting moles to grams. Okay, so let's solve this equation here. So we're going to solve for NV, right? So we know R 0.08206 liters times ATM over mole Kelvin. Okay. And the temperature here is at 0 degrees Celsius, so that's 273.15 Kelvin. And then we divide it by, actually in this example I used 273 Kelvin, so let's just keep it at 273. Okay. And then, oh, sorry, I did it backwards. It should be the other way around. My apologies. So it should actually be P over RT. Right? Yeah, so P over RT. So, whoops. Let's just flip that over here. So on the top of the fraction, we get 1 ATM. So 1.00 atmospheres. And then on the bottom, we get our gas constant, 8206 liters times ATM, mole Kelvin, times the temperature, 273 Kelvin. Okay. So if we solve for that, we will get 0.0446 mole per liter. Okay. So that's our molar volume. So now if we know that we get what for every 1 mole of oxygen, there's going to be 32 grams of oxygen, right? So we can convert that now to grams per liter, and we get 1.43 grams per liter. Okay. So that's not a really, that's a really small density, and that's because it's a gas. Okay, but if you plug this, plug the values in for the density equation here, you will get the same answer. And in this case, it'll be grams per liter because our units for the gas constant is liters. Okay. So this will be grams per liter for oxygen. So we can put oxygen here as well. Grams oxygen per liter. All right. All right. The last example for these lecture slides, and then we'll go into the new material today. Okay. So let's explain why balloons filled with helium at room temperature, 21 degrees Celsius and 1 ATM, float, whereas balloons filled with carbon dioxide sink. Helium's average molecular weight of dry air is 29.0 grams per mole. Okay. Oh, sorry. It should say duh. It should say duh. Sorry. I was supposed to. That's a mistake. My apologies. It should say the average molecular weight of dry air is 29 grams per mole. I will fix that. Okay. So we can actually use the let's see here. So we can actually find the density of each of these compounds, so air, helium, and carbon dioxide, and we can figure out which one has which one has the the lowest density and the highest density, and we can compare with the densities. If it's lighter than air, it will sink, float. Sorry, and if it's heavier than air, it will sink. Okay, so you can actually do the density equation here that I wrote. We could do it for one. Let's do it, or we could do it for all of them. But you can also use this molar equation I solved earlier for each of them as well. And that one actually might be easier to use actually. But let's just use the density equation. So density equals molar mass times P over RT. Okay. So first, let's do it for helium. So let's do it for helium. Okay, molar mass of helium is about 4 grams per mole, 4.00 grams per mole, grams per mole. Okay, and the pressures will be the same, 1.0 atm for everything. Okay, then we have 0.08206 liters atm mole Kelvin. So I'll only show the units for one because they're pretty much the same. And 21 degrees Celsius is 294 Kelvin. Okay. So if we do this calculation, let's do it really quick here. 4 divided by 6. And then divide this. So 48.74. Okay, so we get roughly 0.165 grams of helium per liter. Okay, so now if we do this same equation for all the rest of the gases, CO2. Okay, so in this equation we get we would get the same kind of equation here, 44 this time. So we're going to, 44.0 grams per mole. And then we get 1.0 over 0.08206 times 294 equals 1.82 grams per liter. So a much higher density than helium. And then if we do the same thing for air here, so air, it'll be 29.0 times 1.00 over 0.08206 times 294. And if we do that, we will get 1.2 grams air per liter. So you see here, so we say density of helium is less than the let's write in words, let's not use symbols, is less than the density of air. So it floats. The density of helium, the density of CO2 is greater than the density of air, so it sinks. All right. So that's how we would analyze density. That's why helium balloons, they float up in the air. They're less dense than air, so they're going to float. And so if you had a balloon full of carbon dioxide, it actually wouldn't float. It will actually sink. So if you in the lab, we often use gases that are not helium, and if you put a balloon in them, they won't float at all. They'll just sink. They won't. If you attach a string to them, they won't sink because they won't float because they're much heavier than air. So they tend to stay on the ground. Okay. And yeah, if we wanted to get a gas, to go on the ground, we could use balloons, and that's the way to deliver gas going downward towards the towards the Earth, rather than going up towards the atmosphere. So it can be kind of useful there. Okay, so we're going to move to the next lecture here, and this will probably cover 2 lectures. It's a long one as well, so gases are a pretty hefty chapter. But for this week, please, we're going to we're not going to rush through anything. So please go through these lectures at your own leisure. It's a lot of information to take in. All right, see you in the next video.